Hello everyone, welcome back to part 3 of chapter 29. And the last video was a bit short because we only got through about 35 minutes worth of material, but I wanted to stop because the next set of material is pretty much self-contained, but it might take us a little more than an hour to get through all of it. And so just keep that in mind. Obviously you can see the time stamp for this video, so go ahead and space it out as you see fit. But the main point behind this video is something called Ampere's law, and this is going to be very similar to the Gauss's law discussions that we had back in chapter 23. And if you remember, with Gauss's law, we took a certain amount of enclosed charge Q and related that to the electric flux that passed through the area of that enclosure. And so this portion of the expression right here, that was the term electric flux. And then whatever electric field was produced by that enclosed charge would relate to the electric flux that passed through the surface of that enclosure. And so just as a quick review, if we had a positive charge that was sending out electric field lines in all directions, then we could put a container around this charge. And if we could find a place in space where all the electric fields that were passing through this Gaussian surface had the same magnitude, then we could put all of that information into Gauss's law, and we could derive an expression for what the electric field for that system looked like. For Ampere's law, we want to do something similar, except that we're not going to have a stationary charge in the system. We have to have a moving charge. And that's because the only way that we can produce a magnetic field or magnetic interaction is to have a moving charge. And so the setup for Ampere's law is going to look very similar to what we have for Gauss's law. But instead of an enclosed charge, we will have an enclosed current value. And this implies something to carry that current. We're going to use a wire. Now that wire could be a straight portion of wire, it could be a curved portion of wire. In either case, we have previous descriptions and expressions that tell us what those magnetic fields should look like. And then we need not an electric flux, but a magnetic flux. And paired with that is going to be the magnetic permittivity. I need to move this over a little bit because, as it turns out, our magnetic permittivity actually shows up on the other side of the expression. There's a little bit of a difference with where the permittivity values go. But now we can take the idea of electric flux and we can pair it up against what we would expect for a magnetic flux. Now here's the major difference between the two. With Gauss's law, we had our electric fields passing through a surface area. With Ampere's law, we have a magnetic field that is going to be orbiting around our current. And what we want to do is we want to lay down a path for that magnetic field to follow. everywhere on that path of, in this case, radius r, we want that magnetic field to have the same magnitude at all points on that path. Well, it would make a lot of sense if we just put that path right there where the magnetic field is. So kind of like what we had with our Gaussian surface. We were looking for a location where the electric field would have the same magnitude at all points in space. And so we had to put this surface area around the charge as the container. The reason that we can't do a surface with Ampere's law is because the wire itself continues to extend in both directions. And if we're using the case of an infinitely long wire, then we can't really enclose it with a surface area. But what we can do is we can enclose it with a path. And so we're going to give this the name of the Amperian path, or as the book calls this, the Amperian loop. This is a loop that goes around our current, so it encloses the current. But then we have to add up all of the magnetic field that traverses the path of that Amperian loop. And we've kind of gotten into the habit of using S for arc length and path length. And so that's what we're going to do in the case of Ampere's law. So Ampere's law, it does look very similar to what we have for Gauss's law. And I'm going to put the circle around my integral symbol there to indicate that this does need to be a closed path, similar to the closed surface area integral that we had with Gauss's law. But now that we have Ampere's law set up, it's actually going to be a very smooth mathematical expression to describe what the magnetic field is, some point r away from a current carrying wire. So in this case, we have some current that is going to be traveling up the wire. We can use our right-hand rule to help us map out the direction that the magnetic field should be pointing as it goes around this wire. So take your thumb, point it in the direction of the current. The thumb is the straight line portion that you're going to use with the right-hand rule. And then the curved portion will be the curve of your fingers, and your fingers will have to curve in a direction that goes around the back side of the wire and then around the front. But when that magnetic field gets to this point in space, it will have an orientation that is into the board. When it gets around to the other side, it will be coming out of the board. But at this point, we're not so much concerned with the direction that the magnetic field is pointing at any given location. We want to know the magnitude of that magnetic field. Well, we can go back in our notes and we can look up the magnitude of a straight line wire that we used the calculus derivation to give us, or we can try using Ampere's law. And just like Gauss's law, Ampere's law works very well if you have a symmetric system. And what could be more symmetric than a line and a circle? Because that's what we have. Our wire is a straight line. We have a magnetic field that is a perfect circle. Lots of symmetry in there. And so Ampere's law says after you take care of the dot product relationship, then you can take your integral and rearrange for your magnetic field and you're done. What took us about half an hour to derive using the calculus approach should now only take us a couple of minutes using Ampere's law. So here we go. First thing we have to do is take care of the dot product. The dot product can be evaluated as the magnitude of each vector times the cosine of the angle that exists between those vectors. So let's take a look at those vectors. The magnetic field is going around in a circle, but let's just pick a spot along this path, and we'll give that infinitesimal portion of length a name. We'll call it ds. Now the picture here might be a little deceiving. It's hard to draw 3D on a 2D surface, but as we go around in the circle, keep in mind at this location we're going into the page. So maybe I shouldn't draw the arrow for ds pointing up. It should be pointing into the page. But the point that I'm trying to make here is that as we go around the circle, both ds and our field vector are traveling together parallel to one another at all points as we go around the wire. And if those two vectors are always running parallel to each other, that means we have a 0-degree relationship, and cosine of 0 goes to 1. That brings our Ampere's law expression to this. And I know it doesn't look much different, but we do have to evaluate any of our vector products before we attempt the integration process. Mu naught is a constant. I enclosed, well, that's going to be the current that was enclosed by our Amperian loop. Well, where's our Amperian loop? That's ds. We're going to let our Amperian loop just lie along the path of our magnetic field. And once we've drawn that path, well, our Amperian loop is enclosing the current that is traveling through the wire. And so our enclosed current is I. The last thing that we have to do, we can realize at this point that at all locations on our Amperian loop, we're expecting a uniform magnetic field. And if the magnetic field is uniform, it can be brought out front of the integral. And the only thing left that we have to integrate is the Amperian loop, or the distance around that circle. We already have a radius of big R, and so the distance around this closed loop is just 2 pi r. Now that the calculus is done, the algebra takes over. We rearrange for the magnetic field, and the expression that we get is the same thing that we got through half an hour's worth of calculus derivation. So this is the expression for the straight line magnetic field magnitude. And so, I don't know about you, but this was way quicker than the calculus approach. Ampere's law works very well. So why not use it? Well, just like Gauss's law, there are going to be some instances where Ampere's law may not work as well due to a lack of symmetry in the system. With asymmetric distributions of charge, Gauss's law was not exactly the best in helping us derive the electric fields in a system if we had some asymmetric distribution of currents. And I say currents as a plural because we could have more than one wire in a system, and we would have to add together the contributions of all of those wires to get a net magnetic field expression. Well, we could use this approach one wire at a time, and then add up the resulting magnetic fields. But we have to remember that this is just a magnitude. This does not tell us the direction that the magnetic field is pointing. That direction is going to depend specifically on what point in space you try to measure the magnetic field at. And that's the tricky part, unfortunately. All right, well, if Ampere's law works that well for a wire, for a straight wire, how would it work if we wanted to measure the magnetic field very, very close to the surface of a wire? Or better yet, could we measure the magnetic field inside of a wire? So for that, what we're going to do, I'm going to draw a cross-section of a wire. So this is a very thick wire, and the current, we'll have the current running out of the page, so towards you. So for that, we have a circle with a dot in it, and so my wire will be carrying current through it, and that's going to be true for this entire cross section. We have current that is passing through this wire coming out of the board. Now that cross-sectional area could maybe be described as a current density because we have a current that passes through a given cross-sectional area of the wire. That was a term that we had back in chapter 26. But we'll hold on to this in case we need it later. We might not need it in this case. But for right now, we just want to know what's the magnetic field. Let's start at a point outside of the wire. And we'll assume that this wire is very long and it's a straight wire. We're trying to measure the magnetic field out here at a distance of r. If you use the right hand rule and allow your thumb to point in the direction of the current, so your thumb needs to be pointing up out of the page towards you, and then if you allow the curve of your fingers to map out the direction that the magnetic field is going to travel, we should see the magnetic field orbiting around the wire like so. And I want to know the magnitude of the magnetic field right there at a distance of r. Well, compare this picture to what we just had up here. In this case, I have a very thin wire, but it's still carrying a current of I. I'm still at a distance of r, and all I have to do to get Ampere's law to work is to lay down a path upon which the current can travel. And so that path is going to go around the same path that our magnetic field was going around. By setting up Ampere's law, we're expecting a uniform magnetic field at all points along the path of our Amperian loop. At all points on that loop, the magnetic field and our displacement vectors are running parallel to each other. So that takes care of the dot product. Since the magnetic field is supposed to be uniform at all points, we can bring that outside of the integral. We have a current of I in the wire, so that becomes our enclosed current. And the only thing left is to integrate about the path. To go around the circle, to go around the Amperian loop, is a distance of 2 pi r. And, well, this is exactly the same outcome that we had before. And really, there's no difference in the two pictures other than the fact that I drew the wire as being much thicker. But we're still getting the same expression for the magnetic field outside of the wire. So now the question becomes, how close to the wire can I get and still be able to draw an Amperian loop that encloses the current? Well, you can get right to the surface of the wire if you want. And we'll say that the thickness of the wire is little r. All right, well, right-hand rule again. We have our current pointing out of the page. The curve of our fingers is going to show the magnetic field traveling around the outer surface of this wire right along the Amperian loop that I've just drawn. The angle relationship between the magnetic field and the Amperian loop is no different from what it was further out. Those two vectors are going to be running parallel to each other. And so when I set up Ampere's law right at the surface of the wire, the only thing that changes is the path length. Instead of being out at a value of big R, we're now at a value of little r. There's no additional math that is required. All we have to do is substitute the r value. It is worth noting that the magnetic field is going to be quite a bit stronger at the surface of that wire, but that's because having a smaller r value in the quotient is going to make the quotient bigger. So as long as we're outside of a wire, the magnetic field can be described as a line or a straight wire carrying current. So what about inside the wire? What is the magnetic field going to look like inside the wire? So we'll draw the cross-section of the wire to be larger than what it was before. We'll try and make a better cross-section here. So remember, the wire had a full radius of r, but I want to know what is the magnetic field at radius a. And a is less than r, but it's going to be greater than 0. Okay, well, at a radius of a, there's more than one point in the system where we have a radius of a. In fact, there's an entire path of radius a. The wire itself is still carrying current out of the board, and to help us out with this discussion, I'm going to draw a whole bunch of vectors that are oriented out of the page. And so all of these vectors together indicate the current of the wire. But the reason I wanted to draw a bunch of separate vectors is to show you that not all of the current that is passing through the wire is actually going to be enclosed by our Amperian loop. The reason I need to put my Amperian loop at that radius of A is because that is where I'm trying to measure the magnetic field. Now, our magnetic fields are still going to be orbiting around in this clockwise direction, but we're also going to see magnetic fields inside the wire. Now, why are we seeing these? Well, because we still have current inside the wire. Specifically, we have current that has now been enclosed by this Amperian loop of radius A. And as long as we have current coming out of the board, we will see magnetic field lines orbiting around those current lines. As far as Ampere's law is concerned, the only major difference that we have in our setup is this value right here. Our Amperian loop has no longer contained the total current that is passing through the wire. It's only containing this portion of the current. And that's the portion that I need to figure out. I need to know how much current is actually passing through my Amperian loop. Well, let's take care of this dot product first. I can see that as the magnetic field lines orbit around my Amperian loop, my magnetic field lines and my displacement vector ds are still traveling together parallel to one another. So that takes care of the dot product. We're expecting a uniform magnetic field at all points along that loop, so B can come outside of the integral. We can also take care of the integration around that loop because we now have a path that is equal to 2 pi a. And that means that the magnetic field produced inside of the wire is going to equal mu naught I enclosed over 2 pi a. Now, we could leave it this way, but it's our responsibility to figure out how much enclosed charge, or rather how much enclosed current are we dealing with. And that is something that we can figure out. The total current of the wire is passing through the total cross-sectional area of the wire. And, well, this was what we called the current density right here. If we are to assume that we have a uniform current, or rather a uniform current density, so we have the same amount of current per unit cross-sectional area, then that ratio of total current to total cross-sectional area must equal the same ratio of enclosed current to enclosed cross-sectional area. Now, what do I mean by that? Well, I mean all this stuff that we just highlighted in yellow. There's a certain amount of current that is passing through that yellow cross-sectional area, and that's the value that I'm trying to figure out. The enclosed cross-sectional area, well, that's just the area of a circle with radius A. So our enclosed current is passing through a cross-sectional area of pi a squared. That has to be equal to the same ratio as what we have down here. The total current is passing through a total cross-sectional area of radius r. So pi r squared. If we want, at this point, we could stop calling this current total, and we could just call it the current that is passing through the wire. And this means that the enclosed current, the current that's enclosed by our Amperian loop, has to equal the total current times the ratio of a squared over r squared. If we rearrange what we have here in our ratio expression, this is what our enclosed current is going to have to equal. That value will now be substituted into the expression that we have for our magnetic field. The enclosed charge is now I, a squared over r squared. But we have a squared in the numerator, we have a in the denominator. Mu naught I a over 2 pi r squared. And this is going to be the magnetic field magnitude inside of a wire that is carrying current. And as long as A is greater than 0 and less than R, this is a valid expression. But then that brings up the notion, well, what if we let A equal 0? Well, in that case, your magnetic field is going to tend to 0. And that means we don't have a magnetic field at the center of the wire. And that's because at the center of the wire, we could either argue that there's no magnetic field to enclose by an Amperian loop, or a better argument would be that the length of the Amperian loop to surround a single point is 0. And so our magnetic field would be 0. The other thing we could try is, what if we let A equal R? So what if we went back to the surface of the wire? In that case, if A is equal to R, the expression will revert back to the straight wire current expression. And that should be expected, because whether we approach the surface of the wire from outside or inside the wire, we should get the same value of magnetic field at the surface of the wire in either case. What we can't do is we cannot allow A to equal anything larger than R, because to do that would imply that you have current passing through a cross-sectional area that is outside of the wire, and that is not physically the case. I cannot extend A outside of the wire because A is being used as a ratio measurement for current, and I don't have current outside the wire that can be enclosed. Long story short, if you're outside of the wire, you treat it as a straight wire and you use the straight wire expression. But if we're inside the wire, then we need to use this expression so that we're using only the enclosed portion of that current. All right, well, that was something that the calculus approach did not tell us. The calculus derivation didn't allow us to solve for a magnetic field inside the wire, but Ampere's law did. Now, if Ampere's law can work for a straight line of wire, can it work for a curved portion of wire? And the answer is yes, it can be used. But I don't want to limit myself to just a single loop of wire. Instead, I would like to see if we can apply this information to something a bit bigger, like a coil. If we have a coil of wire, also known as a solenoid. So this is going to be a loop of wire. Each loop will have the same radius value of R. There will be a length of L. And there's a certain number of turns per unit length associated with this coil. Or we could just say that N is the number of loops associated with that solenoid. And so I think this book uses little n as the ratio. I'm double checking my notes over here. I want to make sure that I have the same notation. Sorry, give me one more second here. Actually, it looks like this book might be using little n as the number of loops. Well, in that case, we can just use n over L as the number of loops per unit length of the coil. And this may not seem like an important ratio right now, but we need to keep in mind that there are physical limitations to being able to build a loop, or a solenoid, I should say, because the wire that we're using has a certain thickness associated with it. And if I want to stack one loop of wire on top of another, on top of another, on top of another, that's going to determine the overall length of that solenoid. If I use a thicker wire, oops. It's going to try to use a thicker wire. Let's see here. Try this. There we go. If I use a thicker wire, I'm not going to be able to stack as many loops in the same length as what I could with a much smaller diameter of wire. And what we're going to find out is that with every loop in our solenoid, that is going to increase the strength of our magnetic field by that scalar value. So the more loops that we have inside of a solenoid like this, the stronger the magnetic field that we're going to get running through the center of that solenoid. And we can show that using, surprise, surprise, Ampere's law. So let's take a better picture of this solenoid. So we're going to have a certain number of loops. And don't worry about trying to count these loops. We'll just say that the number of turns is n. But I'm going to look at a cross-sectional cut of this solenoid. So imagine that you have a knife or a saw blade, and you're going to cut straight down through this solenoid, and expose the cross-sectional area of this coil. And so what you're going to get when you do that is you will only be able to see the cross sections of the wires as they wrap around to the top of the coil and to the bottom of the coil. So we can kind of imagine that the coil starts right up here and then wraps around to the bottom and then comes back up to the next and then wraps around to the bottom and then comes up to the next and then wraps around to the bottom. And so every time the coil either goes into the page or out of the page, that is the cross section that we're looking at. So let's say for our purposes, every time the coil carries the current out of the page, that's at the top cross section. And then every time the coil carries the current into the page, that's at the bottom cross section. So our wire brings in the current comes out of the page with the first turn in the coil, goes into the page, curves back up, comes out of the page, curves back down, goes into the page. And so we keep doing that to make the full coil of the solenoid. Well, the reason that I want to see these cross-sectional cuts is because every time our wire carries current into and out of the board, that's another amount of enclosed current that we need to consider for Ampere's law. We'll set up Ampere's law, and the location where we want to measure our magnetic field is going to be right through the center of this solenoid. So this is where we want to measure the magnetic field. There's two things that we need to do at this point. First, we need to figure out what our Amperian loop is going to look like. So what kind of path are we going to draw for that magnetic field to follow? And that's usually very straightforward. We're just going to let our Amperian loop follow the magnetic field. But we also have to enclose some current. We haven't enclosed any current yet. And at this point, my options are two. I can either take my Amperian loop and curve up so that I can enclose all of the top portion turns of the coil, or I could curve down and enclose all of the bottom portion turns of the coil. In either case, I'll be enclosing the same number of turns. I haven't counted, but let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so at least I got the same number of turns on the top and the bottom of the coil. But the point that I'm trying to make here is that I can't enclose both the top and the bottom crosscuts. And I wouldn't want to, even if I could. Because if I did that, I would end up with a net enclosed current that would be equal to 0. And the reason for that is because I would have the same number of currents coming out of the page as what I have going into the page. remember with Gauss's law, we didn't want to enclose a net charge of 0 because then we wouldn't get an electric field. In the case of Ampere's law, we don't want to produce a net current of 0, otherwise we're not going to be able to use Ampere's law. But this will actually work. I've enclosed, in this case it was 9 cross sections of current. So this would imply that the number of turns associated with this particular coil is 9, but again, we're going to keep this in a general form. We'll just say that the number of turns is n. And so that means my enclosed current is just n times the current that's traveling through the wire. So there's my enclosed current. It's Ni. Now we need to take care of the dot product between our magnetic field line and our displacement vector. Now really the only place that we need to concern ourselves with is where the magnetic field is traveling, and that's through the center of this coil. On these legs of the Amperian loop, if I travel up and down those side legs, well, those side legs are perpendicular to the magnetic field line, and so hiding inside of that dot product is a cosine relationship, and cosine of a perpendicular angle is 0, so the left and right sides of the Amperian loop aren't going to contribute. And then outside of the solenoid, well, I don't care what the magnetic field is out there. The only place where I care is right through here, right through the length of the solenoid. And so integrating just through the center of that solenoid, the magnetic field and our displacement vector are running parallel to each other. That's an angle relationship of 0. Cosine of 0 evaluates to a 1. Our magnetic field, we're expecting that to be uniform through the solenoid, so that comes outside of the integral. And the last thing we have to do is integrate about the path through that solenoid. Well, we should already know how far we have to go through that solenoid. It's the length of the solenoid. So that integral for ds just becomes L. And now is where we can see the importance of measuring the number of turns per unit length for a solenoid, because it's actually going to play a part in the strength of the magnetic field that passes through that solenoid. Now, the obvious outcome for this would be that, well, the more turns you put with your solenoid, the stronger of a magnetic field that you're going to get. But the more turns you put in, the longer of a coil that you're going to have to produce. Because remember, each coil has a certain thickness associated with it, and that's going to contribute to the overall length of the solenoid. And as the solenoid gets longer, well, then the magnetic field starts to get weaker. So is there some kind of a balance between the two? And the answer is probably, but it's going to depend on the thickness of the wire that you use. And so there are a lot of different gauges of wire out there. Typically, the higher the gauge, the thinner the wire is. But Maybe you could get yourself a really, really, really thin wire, and then you could just pack in a whole bunch of turns and get a really high value for N while keeping the value for L really low. And so would that give you a really strong magnetic field? It would, except now what have you done? You've used a really, really thin wire, and the path that all of your charges have to follow to get through all of those multiple loops is really, really long. So what have you just done? Well, you've provided a very long path for your current to travel through and a very small cross-sectional area associated with the thickness of the wire itself. And so you have just caused the resistance of the wire in the solenoid to skyrocket. And what is resistance going to do? Well, it's going to kill your current. So even by trying to maximize this ratio, the unintended effect is going to be that you're going to kill the current, and that's going to cause the magnetic field through your solenoid to end up being smaller. So it's one of those situations where you try one thing and it causes something else to break. And so is there an optimal case scenario of number of turns to unit length to thickness of wire? And again, I'm going to answer with probably, but that's something that you would have to do as an engineering project to see what dimensions of coil versus length of wire, and even the material of the wire that you're going to use are going to play a part in determining how strong of a magnetic field you can produce. So one last topic for an application of Ampere's law, and that is that we're going to take our solenoid and we're going to wrap the solenoid in a circle. So what's that going to look like? Well, it's going to look something like this. So we're going to have a loop of loops. And this particular construct is called a toroid. And really we just have a solenoid which has been wrapped around in a circle. And what we want to know is if we have current running through these loops of wire, what kind of magnetic field is it going to produce? And that magnetic field would have to travel through the center of all of those coils. And that's what we want to find. So once again, we'll get out our knife and we will cut straight down through this construct, exposing a cross-sectional cut. And what that cross-sectional cut is going to look like, you'll have to give me a moment to draw this. We're going to get cross-sections of wires where the current comes out of the page. And then we're going to have just as many cross-sections of wire carrying current into the page. So again, this is going to relate to the number of turns associated with this toroid. And I can try segmenting these wires. Have to try to make the same number of cross sections on the outer circle as we do the inner circle, because what's going to happen is, let's start right here and say we have some current coming out of the page. That current is going to follow the path of one of the loops into the page, and then wrap around and come back out of the page, and then wrap around and go back into the page, wrap around, come out of the page, go back into the page. And so we're just going to keep following this path going in and out of the page, but noting where those cross sections are going to occur. And the reason we want to do this is, again, because we need to know how many times we are going to end up enclosing the current of the wire. We have a single current of I that is going to be running through all of these wires, but since we're trying to map the magnetic field that goes through all of these coils, let's see here. Yep, the magnetic field will in fact go this way. And since this is the direction of the magnetic field, we'll go ahead and place our Amperian loop right along the path of the magnetic field line. Magnetic field line and the Amperian loop are running parallel to each other as we go around the toroid. We will set up Ampere's law. First thing we'll do is take care of the dot product. Since B and DS are running parallel to each other, that dot product is hiding a cosine that will evaluate to just a 1. Now the enclosed current. How many currents did we enclose with our Amperian loop? Well, here's our Amperian loop. And what did we enclose with that Amperian loop? Well, we enclosed all of these cross sections of current. How many cross sections are there? Don't count them, because they're right there. The number of currents that we will enclose will be that scalar value that is associated with the number of turns. So we have mu naught Ni for the enclosed current. We are expecting the magnetic field to be uniform at all points at whatever this distance is from the center of the toroid. We'll call that distance R. But that implies that we should probably put in some other limits, like an inner radius of the toroid, A, and an outer radius of the toroid, B. So we want R to be somewhere inside of those loops. That's going to be one condition there. We didn't have to worry about that with the solenoid because we knew that we were passing through the center of the coil. And so we didn't have to worry about that. Also, you might notice for the solenoid expression, the magnetic field for the solenoid doesn't depend on the radius of the coil, which is kind of interesting. But for the toroid, well, for the toroid, when we go to integrate the path length for ds, that path length does depend on that radial measure. And that path length is going to equal 2 pi r. It's just a circle. We're done with the integration. We'll let the algebra take over. We have mu naught ni over 2 pi r. And there is the magnetic field. Can't spell today. Try that again. That is the magnetic field magnitude for the toroid. If we compare that to the magnetic field that was produced by the solenoid, that was the expression for the solenoid. Well, how is that really any different from what we have here for the toroid? Especially if we made the toroid from the same solenoid. Is there really any difference between these two expressions? And the answer is no, because if you consider the path length here, which is 2 pi r, well, isn't that path length just the same as the length of the solenoid? If you take the length of the solenoid and you wrap it around in a circle, well, what's the length of that circle? It's just the same thing. And well, if we pair that together here, we've got n over length. It looks like there's another condition where we are going to be limited by the number of turns that we can fit inside of any toroid. But the major difference between these two expressions is that when it comes to the toroid, we don't have to limit ourselves to measuring the magnetic field right at the center of the toroid. We don't have to measure things right here at R. We could move out a little further if we wanted towards the outer wall of that toroid. You know, we can get really close to B if we wanted. In fact, we could probably get right up to equal that value of B. If we did so, the magnetic field would reduce in magnitude. But at the same time, we could also sneak in a little bit, get towards the inner wall of the toroid, towards A, and in that case, the magnetic field would get stronger. Can you go outside of the toroid and measure a magnetic field? Well, let's see. Let's clean this up a little bit, if I can. So here's our toroid. And the question I've posed now is, can we measure a magnetic field outside of the toroid? So can I measure a magnetic field right here? Well, try it. Try placing an Amperian loop at that radial value. And if you try that, what you should note is that by enclosing the toroid with your Amperian loop, you have just enclosed equal and opposite numbers of cross-sectional currents. You now have the same number of currents coming out of the page as what you do going into the page. And so you've just achieved a net enclosed current of 0. And if you do that, well, there's no point in continuing through the rest of the math over on this side, because your magnetic field would then be 0 outside of the toroid. So what if you tried measuring the magnetic field inside the toroid? And when I say inside the toroid, I mean really inside the toroid. What if you measured a radius r from the center of the toroid, where r is less than a? And a was that inner measure. Okay, try it. Place an Amperian loop at a radius of r, and how much current did you enclose? None. Because there is no current in the very center of that toroid for you to enclose. And again, with no current enclosed, there's no point in trying to solve for the magnetic field because it's going to be zero. The only place where we're going to find a magnetic field for the toroid is going to be between the physical limitations of those loops. So that brings us to the end of chapter 29 material. So we were able to squeeze all this material in with just 3 videos, which is good. Chapter 29 is actually one of the shorter chapters of this book. And so when we come back, we'll start chapter 30, which is going to be the last chapter for this physics course. So we'll see you back for chapter 30.